Hello everyone, here is our group presentation. Our project title is Visualizing the Loss Landscape of Deep Neural Networks. Neural networks algorithms which give a specific structure, and the structure includes that neurons in a layer structures, and the neurons take inputs and propagate the signals from the previous layer to the next layer. And throughout the propagation, signals are modified by the weight W. We can also call them parameters of this model. So the neural networks are widely used in computer vision, natural language processing, and many other fields in the artificial intelligence. In order to assess the performance of the neural networks, one thing that people commonly do is trying to analyze or visualize, in our case, the optimization landscape. Since the neural network have a lot of parameters, it actually lies in a very high dimensional space. And the loss landscape also lies in that very high dimensional space. So it is hard to visualize them. So we would like to give a low dimension snapshot of that space, such as this three-dimensional plot. And this plot basically is higher the z-axis is higher the training loss, which is just higher the error. So the neural networks is a common used way to train neural network is gradient descent. People normally use stochastic gradient descenting for neural networks. That's a kind of gradient descent. And the general ways to minimize the loss function, there's such as mean squared error or cross entropy. It's just a measure of error. And you go around the steepest direction, which is direction of the gradient.
So the generalization gap is another important term that we use when we evaluate neural networks once they are trained. And this measures how well the neural network actually performs on data that it's never seen before, as opposed to the data that's seen in its training process. Often neural networks can memorize training data and labels, but it doesn't accurately make predictions on data that it hasn't seen before. So for example, if a model has been trained to classify different kinds of apples, for example, maybe it classifies all the apples in its training set very well, but if it sees an apple never seen before and classifies it wrong, then it might have poor generalization. And in this figure, we can see that this neural network has not very good generalization because it has full 100% accuracy on the training set in the blue and almost zero loss, but it has less than 60% accuracy on the test set. So the generalization gap for accuracy is 41%. And it also has a very high loss for the test data. So it has a very large generalization gap for loss as well. So all of that was some background on how neural networks work and how we evaluate and train them. So for our experiments, we produced a measure of sharpness along one-dimensional plots. And to do this, we plot the training accuracy of the network along a random vector through our minima that we've chosen. And as you can see, the accuracy is 1.0 at 0 along the x-axis for both of the figures, because 0 represents the actual minima itself. And to see the sharpness, we are taking the training accuracy, which is the y-axis, at the points plus and minus 0.15 along the random vector, and taking the sum of that. So on the left side, we have 0.94 times 2, and on the right side, we have 0.29 times 2. And that is our quantitative measure of flatness rather than sharpness, because a higher value, as seen on the left, correlates with a much flatter and hopefully well generalizing minima. And from that measure, we have plotted this flatness that we've defined for many different models that we've trained that have various levels of generalization ability, which we measure in terms of test accuracy, because they are all fully trained on the training set. And we find a very strong linear correlation between this flatness and test accuracy. And it's surprising because we usually think of sharpness in terms of a very local region when we think of things like properties of the Hessian, for example. But these random vectors extend much farther into the parameter space. And so it's surprising that there's still so much information that we can learn from them at a larger region, and it's worth looking into and studying more in the future. And speaking of Hessians, I'll let Jupiter take the next.
Yeah, so one way to understand the geometric properties of the loss landscape is through looking at sharpness or flatness, as Annie has just introduced. Another common way is to look at the higher order information, such as the derivative, the second order derivative, and etc. As we all know that we use gradient descent in the optimization process, which utilize the first order derivative or the gradient. But at the minima, we all know that after it converges, the gradient is 0. So in order to get a local geometric properties, we switched our focus onto the second order property, which is the Hessian. The Hessian basically represents how the changing rate of the gradient is a matrix in the following form. So these are some of the empirical results from the previous studies. Well, first of all, as many empirical experiments have proved that the top eigenvalue as the local sharpness is a very good indicator of the generalization gap. And also previous works have also shown that the gradient lies in the dominant eigenspace of the Hessian. So that may also tell us that the Hessian itself is very important in the optimization process. And also there are many observations claiming that there's a gap between the top C-1 eigenvalues and the other eigenvalues. Many claim that that is due to the intrinsic dimension of the data set. Most of our works have been focusing on is the decomposition of the Hessian. Here we're focusing on the layer-wise Hessian, which is the Hessian only considering the cross terms of the neurons in the same layer. Under our theoretical analysis, we have seen that the Hessian can be decomposed into two terms. The left one, UTAU, which is related to the parameter, and the right one, XS transpose, which is related to the output. So that way, a very gigantic Hessian, which is usually computationally invalid, we're able to decompose it into like two small matrices, which can be computed in a very fast way. We actually checked how accurate our approximations are. And as we can see for the top C-1, which is like 9 eigenvectors, the approximation of the two components calculated separately versus the real Hessian has a very high overlap. So that way we can provide a reasonable estimation of the Hessian itself. So for the future directions, there are many interesting stuff that we can do, and apparently our research has not stopped. We'll continue our research focusing on, for the sharpness, that part Annie has been introducing, we hope to provide a more accurate generalization gap estimate on different definition of sharpness. And also for the Hessian part, we look forward to use the information that the Hessian has to provide some insight in terms of generalization and optimization. And hopefully we can have a better generalization bound or an accelerated optimization algorithm. So that's all for our presentation. Thank you for listening.